Alright, so we're going to go ahead and get into chapter 1 today. This thing will open. And it's opening 3 of them. Okay. So, need to up my volume.
Elevators, your chairs in the office, every time you go down the lever, that's pneumatics.
I guess part of the beauty of fluid power is it's such a simple thing.
What is the... Okay, so volume, bring that back, and widescreen it, play.
Fluid power, elevators, your chairs in the office, every time you go down the lever, that's pneumatics.
I guess part of the beauty of fluid power is it's such a simple thing. It's, you have a cylinder, you have a pressurized liquid that's pushing one way or the other. So fluid power, it's a way to move really big stuff really fast in a really small package.
It's using a gas or a liquid under pressure to move a piston or a shaft to do work.
Just like you would use a lever to transmit energy or masses through a mechanical means, the lever gets replaced by a fluid lever. And you can compress or expand that fluid to create more or less lever forces on your end result.
I can see it, I can intuitively understand what's going on. It's at a scale that makes sense to me.
You can touch it, you can feel it, you can see it. Fluid power is on the human scale.
I can see a valve shifting, I can see a pump turning, see oil moving inside of a hose.
It touches our daily lives. You find it in entertainment industries, you find it in large construction machinery, in agricultural equipment, and in a nutshell, it's a lot of power in a very tiny package.
And the fact that this fluid power component systems are so powerful really has a lot of kind of fun associated with it. So you see big things moving and moving at high speed, and it's very impressive.
So like I said before, fluid power systems are a workhorse, especially hydraulics. Hydraulics are well known for being a lot of power in a little space. Where did this go? There we go. Oh. Maybe I'll have to jump in here.
Machines and tools. They help us to do work. But do you know that many of these are pressure machines which use either the hydraulic system or the pneumatic system? Let's first look at the hydraulic system. But in order to understand what a hydraulic system is and how it works, we have to know 2 facts. The first fact is that when a liquid is enclosed in a space and a pressure is applied to the liquid, this pressure is transmitted equally to all parts of the liquid.
So think about your shower head or your garden hose. No one opening gets more than the others unless it's blocked or has a obstruction of some sort, right? Every single one, if you get a brand new sprayer or a brand new shower head, every part of it is working exactly the same as the others, right? So this is one of the first principles.
This principle is illustrated using this pressure syringe. When the piston is pushed down, water squirts out uniformly in all directions from the holes of the flask. The second fact is that it is hard to compress a liquid. If you try to squash a volume of liquid, you still have that same volume, however hard you try to compress it. A hydraulic system is one that uses the pressure of a liquid to perform mechanical work. Let's look at this device. Two syringes, A and B, of equal size, are connected by rubber tubing. If pressure is exerted at syringe A, the same pressure will be transmitted over to syringe B. We also observe that the water from syringe A will move to syringe B, as shown by the upward movement of the piston in syringe B. This demonstrates the two facts which we have just discussed. That is, firstly, when a liquid is enclosed in a space and a pressure is applied to the liquid, this pressure is transmitted equally to all parts of the liquid. And secondly, liquid cannot be compressed.
So real quick, what happens when you compress a liquid? Yes. The other thing is that you cannot compress a liquid. You cannot, if you put too much pressure on a liquid, it finds ways around your seals. That's why one of the most memorable things my brother ever did, and you have to understand, my brother's not the smartest cookie in the box. He borrowed my dad's old truck, and he ended up blowing every seal in it. How'd he do that? I think he put about 8 quarts of oil in it, and something that only took about maybe 2. So he overfilled it, which would have overpressurized it, which blew every seal in it. It had nowhere to go. Exactly, it had nowhere to go. Liquid is not, it's what makes hydraulics so good, is that you cannot truly compress it. It does not readily, it's kind of like whenever you do a belly flop, or you sit there and you slap your hand on water. Does the water move for that 1 minute? No, it doesn't. It's able to actually be almost solid. And that is what makes water, or makes fluids so good at this, is that they don't compress any further than what they can. Does that make sense? So just to kind of...
Hydraulic system makes use of these two facts. It can be shown mathematically that if we make one of the two pistons much larger than the other, then the larger piston can raise a larger load. The hydraulic system can therefore be considered as a force multiplier. Do you also notice that the small piston has to move a larger distance than the large piston? In most cases, oil is used as the hydraulic liquid, as it can lubricate the moving parts of the machine as well. The hydraulic principle is used in many devices, like the hydraulic jack used for lifting cars at the service station. Notice that the serviceman has to exert a force on the piston many times before the car is raised by a small amount. Thanks to the hydraulic jack, lifting a car for servicing is no longer a problem. One of the most important components of a car is the brake system. But do you know that the brake system of a car also works on hydraulics? Let's take a closer look at the brake system of a car. When the driver presses on the brake pedal, the oil in the brake system transmits this pressure and moves these pistons. This will cause the brake pads to press against the rotating disc of the wheel. Hydraulics is also used in many heavy machinery in the construction industry, like this loader. Can you see the moving pistons in action? Machines using the hydraulic system are capable of moving very heavy loads. This is a dumper. It also works on hydraulics. The excavator is another hydraulic machine commonly found at construction sites. The hydraulic system will cause pistons to move a part of the machine back and forth. Imagine what it would be like if all this work had to be done without the help of these hydraulic machines.
Okay, I think that's about enough of that. Get back to what we need to get to. So hydraulics, again, you're dealing with fluids that are not really compressible. Again, it goes back to anytime you've ever, let's say a water bottle. Okay, can you compress a water bottle when it's full? Not without blowing the what? Not without blowing the top off, blowing the seal, right? That's the great thing about hydraulics, is that you can exert a lot of pressure and move fluid. The only thing is, if you overpressurize the system, things happen that you don't intend. So hydraulic and pneumatic systems must store a fluid under high pressure. Now, we do call pneumatics a fluid. Why? It handles gases, which are considered a fluid. Gases fall under the same principles as the fluids do. Pneumatic uses air, but air follows the same principles as any liquid you can find. It volumetrically takes up space. It's able to move very easily, right? It can take the shape of any container that it's in. Is that not the three basic principles of a fluid? Yeah. So as far as safety goes, anytime you're dealing with oil lines or air lines, you need to relieve the pressure and discharge any accumulation that might be there. Why? Because you never know what's in there, what temperature it is, or what's going on with it. You don't want that on you, right? That's not really a good idea. So 3 kinds of hazards exist: burns from the hot, high pressure spray of fluid, bruises, cuts, and abrasions. This can occur from flailing hydraulic lines, or slips, trips, and falls. Those are never fun, right? And injection of fluid into the skin. Now that is especially dangerous. How many of y'all actually work on your car? Okay. One of the most dangerous things you can do is lay in a puddle of what? Of anything, right? If it ain't water, you don't want to sit in it. The reason I say that is because I've helped my dad numerous times work with antifreeze or oil or transmission fluid. That stuff, you sit in that for long enough, it'll make you feel sick the next day. Essentially, what your skin is doing is absorbing that fluid. Now think about if your skin actually gets injected with the fluid. That's going to make you sick, probably for days, if not longer. That chemical buildup in your body, if your body can't handle it, will make you really, really sick. So you definitely want to be very wary of those kind of situations, guys. Any system you ever come in contact with is going to need maintenance, right? I don't care if it's mechanical, electrical, hydraulic, pneumatic, whatever kind of system you're dealing with, it's going to require maintenance. Okay? Because otherwise, what's going to happen to the machine? It gets into disrepair and it breaks. Okay? So, when it comes to all that, you definitely want to be very careful of what you're dealing with and make sure you're doing it safely. The best thing you can always do is make sure you've completely discharged any and all pressure. Why? Because you don't want stuff just kind of flailing around. A. B. You don't want anything that's in it to be spilling out all over the place. Talk about, at the very least, a mess. It's just something you pay attention to. And you also want to make sure any couplings of high to low pressure fluid components and pressure relief valves, you want to be very aware of where pressure relief valves are at all times. Why? Because they pull the pressure off the system. For hydraulics, generally, if you're relieving pressure, you're dumping it to the tank. Why? Because all fluid needs to go to tank. With pneumatics, if you are using a pressure relief valve, you're venting. Why? Because, well, we don't have to send it to tank. We can just release it into the air. It gets to go free. Okay? Any questions on safety? Whenever you build your circuits, one of the biggest things I prefer y'all do is make sure you depressurize before you start messing with any components. Okay? That's a very big one, guys, and that's because I've had more than one person take the air hose out and that thing starts flailing around and slaps them in the face. Now that's all fun and games until somebody loses a... Yep. It's always all fun and games till somebody loses an eye, right? Huh? Yes, then it's a safety briefing. And a lot of people get in trouble. So let's not do that. So preventative maintenance. So we need to periodically check for leaks and worn hoses. Why would we need to worry about worn hoses? Well, because though we don't think of how to say this in a way that is kind of fun, if you consider the Grand Canyon, what carved it? Water. And that's not even fast running water, it's slow running water, right? So what do you think fluid does to hoses and pipes over time? Whether it's air or an oil. It wears out the inside, right? Because small particulates and things like that will get in there, or just wear and tear over time. You know, you get weak spots. So you need to be periodically checking for leaks and checking your hoses, because otherwise you'll end up with, and another thing you can end up with is cracks. You know, think about the humidity and then think about how dry it gets in the winter. Every single one of us has probably got chapped skin, chapped lips, and chapped everything right about now, right? Because it's been back and forth on the weather, but mostly it's been dry and cold. Hoses and everything like that suffer the same problems we do. Only thing is, we don't think to try and protect them in any kind of shape, form, or fashion from that kind of thing, right? So it's up to us as preventative maintenance people to check them periodically and make sure that nothing looks like it's going to have an issue in the near future. Does that make sense? You want to keep any and all contaminants from hydraulic oil and replace the filters periodically. This is something that's not always done, is replacing the oil. I know a few places that have said that they never have replaced the oil in the entire time that they've been there. And this is people that have been working there for 5 to 10 plus years. At which point you sit there and ask yourself, why? Well, generally it's because somebody is not wanting to spend the money on something that they think is not important. It's your job as maintenance to convince others that it is important, right? It's your job to sit there and say, hey, boss, we have not replaced this in God knows when. We don't know what this is doing to our pistons, but that's going to be a very expensive replacement over time, right? Do y'all agree with that? So it's your job as maintenance to convince your bosses and to convince people that know what's going on why you have to replace this. If they don't want to, convince them of the cost it's going to cost them to have to replace everything in the system from the contaminants. It's one of those things of you don't always want to take your car to the shop and get the oil changed, but you need to. It's an unavoidable thing you have to do. And a lot of businesses don't consider that. You know, kind of like the air filters in your house. How many of y'all replace those on a regular basis? But y'all know what I'm talking about. That you have to replace the filters every so often in your air system. Why? Because those things will get nasty and dirty, and then all of a sudden your efficiency stinks. If they get nasty and dirty enough, they will shut your system down. Let them go even longer than that, and they can actually become a potential fire hazard. So you need to make sure you're replacing your filters periodically. It needs to probably be whatever maintenance schedule is given to you when you get the equipment, you need to follow it. You need to make sure those filters are replaced religiously, because otherwise, who knows what happens if you don't replace the oil filter in your car? Huh? It clogs up. What happens when it clogs up? It tears up your engine, right? Pistons will seize up. The very worst is that the filter that is in there can shred itself completely and get into your engine, and then you are really sunk. Yep, it can be made out of paper, it can be made out of nylon mesh. None of it's a good thing. So thus, we try and make sure they're changed on a regular basis. Agreed? All right. So we need to make sure that any and all cylinder rods are coated with protective lubricants. This avoids rust issues. We don't like rust. Why? Mm-hmm. So when you have rust, you're going to have breaks in your seals. The interior of the cylinder is going to start really tearing up. Rust is a severe contaminant, so you're going to risk the rest of your system. There's all sorts of bad things about rust. We don't like rust. Rust is a bad thing to have. Okay, just to digress on that. Oh, sorry. So fluid power. Fluid is the use of a confined fluid flowing under pressure to transmit power from one location to another. That is the very definition of fluid power. Fluid itself is something that has no fixed shape and yields to pressure. Okay, so that's why we consider air a fluid. Okay, so the main advantages of fluid over electricity are that the actuators can be stalled without damage. In other words, we can leave them out there and it will not hurt them. We can have actuators that are linear or rotary. You actually will be working with one. It's a rotary motor. It's an actual motor, a pneumatic motor. Actuator speed is very simple to control because we have what are called, what? Anybody know what they are? We can flow control valves. We can control the flow into and out of actuators. The great thing about it is that we have force multiplication, so I can do a lot with a little. Take the floor jack for a car or a big truck, right? I'm only weighing about 200 some odd pounds. The truck weighs about 200 tons. I can lift that with a floor jack. Takes a little effort. Okay, I'll take that back. It takes a lot of effort. But I can lift that off the ground so that I can change a tire or get under it to do work, right? You have fast actuator direction. Think about how fast, not only can I get that thing up, but I can drop that sucker back down so that I can move on to the next job. Now, technically, you're not supposed to just absolutely drop the truck off the jack. It's a bad idea. But if you wanted to, you could. So we have two areas in there, hydraulic and pneumatic. The main one we'll work with in lab is pneumatic, but we do have a hydraulic trainer I'll be letting y'all work with. So it's easier to produce linear motion with fluid because we have linear actuators. It does not take very much to get a linear motion. Fluid likes to travel in straight lines. It also does not mind traveling in curves. It can do it whatever direction. Getting electrical energy, sometimes you can have a little issue with it. It can transmit power in much smaller spaces. It's just really what's great about hydraulics is that I can use a 2-inch piston to do something that for electrical I might have to use a 6-inch plus. With pneumatics I probably have to use a bigger piston on that one. With hydraulics I can shrink the size no problem. It does a lot with a little. It's a lot safer. Why? Well, because unless you have an open flame and you know for a fact that the fluid is flammable, most fluids are safe. Okay. Fluid, you don't end up with that electrical spark. Like we talked about last time, if you have ever held onto a power tool where you can see the electric motor in the back and you hit that button, what do you get to see coming out of that motor? You get to see all sorts of pretty sparks. Which if you really think about that, that's actually kind of terrifying if you're using it in a place where you are in a flammable area. Right? Kind of sort of terrifying. Versus something like a pneumatic tool, which does not do that. Using compressed air to... has anybody got a compressor and a bunch of air compressed tools at home? Or have ever worked with those? They're a lot of fun. And they're very safe. Well, they're safer in a lot of different environments. They're safer in a far bigger variety of environments. How about that? We'll go with that. With fluid power systems, it's simple to control the direction, speed, force, and torque. Sort of like you cannot let an electric motor keep running while you're trying to run it forward and then just switch it over to reverse. It don't work like that, does it? It is not like that. So, but fluid systems, we can do that all day long. If you've ever used a pneumatic impact wrench, that's what I was trying to say. You can put that in forward, you can put it in reverse, and you can do it both at the same time. I've worked with it a couple of times. There's a few of those you can do that with. Kind of cool. Pressure can be held constantly without applying significant amounts of energy. So let's say you have an air tool, you leave it on all night. Is your compressor going to be running every time you turn around? Are you going to have a high power bill? Not really. Not as high as what you would think. If your compressor is working efficiently, let me put that caveat in there. If your compressor is working efficiently, you won't have too big a problem of it running. Now, if you have not drained your compressor recently of any and all fluid that's in it, if your compressor is several years old and has never been serviced, so on and so forth, yes, it will run all night. Yes, it will suck up your power bill like crazy. And yes, you will have to probably pay for that later. However, a lot of the time, pneumatics and hydraulics can stay pressurized over the whole day, and it doesn't bother it too bad. With hydraulics, you don't want to leave it pressurized over time because that can wear out the seals. But at the same time, it's not going to damage it irreparably if you leave it overnight or something. It can hold on to that pressure as long as you're not continually applying pressure behind it. Put that out. Say that. Okay. As long as you're not continually pressurizing it. So let's say this was full and I had this sealed off, right? And I continually pressurize it, then you're going to end up breaking your seals. But if you just happen to leave the fluid in there because you decided you were going to clean up tomorrow, that's not going to damage it. Okay. And power is much easier and more cost effective in applications that require pressure and position control. So let's talking about car jacks. You have the big ones that are actually able to hold a whole car off the ground so mechanics can get up under it, right? You think those are ever depressurized? No, we actually use the pressure to lock them in place up off the ground. So that's where we say, it can be held constant without applying actual extra pressure. We can lock the actuators in place. And since we need pressure and position control with something like that, it's a lot easier to do it than with an electric most of the time. All right, so actuator advantages. So with actuators, these are devices that convert pressure into motion. They are compact and have high energy potential, stalled for extended periods, we've talked about so far. Instantly reversible because I can take it all the way up. Oh wait, no, that's not the car we need to work on today. Bring it all the way back down 5 seconds later, right? And we can vary the speed of these any day, all day long. All we have to do is mess with a valve, which you'll be playing with whenever we get to that particular portion of all this. Of course, you always have the standards committees, because everybody has to have standards. Everybody wants to have standards. So you have NFPA, National Fluid Power Association. You have the American Society for Testing and Materials, the Society of Automotive Engineers, the American National Standards Institute, the International Standards Organization. Okay, we're going to talk a little bit about all these. But first of all, does anybody want to take a break? Are y'all good? All right, let's at least get through the standards and we'll take a break after that. So the Fluid Power Association, these guys determine cylinder sizes because why? Well, let me ask you this. Why do we have standards? So everybody uses the same thing. What else? So you don't have a wide variance of everything. A 2-inch is a 2-inch is a 2-inch. Period. If you have somebody with they're putting threads on these cylinders. Well, you don't exactly want, 2 million different types of threads on these because God only knows what you have to go find to get threaded onto it. So standards organizations are there to, I guess the best way to say it is they are there to protect the consumer. Because otherwise, think about your car. Do you want to have to take it to a specific mechanic at a, in the middle of nowhere? So let's say you have a well, we're not going to talk about Mercedes. Mercedes is a very high end and very particular. So let's say you have something common like a Mazda. I'll use my car. If I need an oil change on my Mazda, I don't want to have to take it to the dealer. I want to be able to take it down to Express Oil Change and say, you know what, I don't feel like driving all the way out to Pelham. Can you please change my oil? That's where the standards come in, right? Because the people that make the standards say, well, there's no problem with that. It's not Mazda that makes these oil canisters. I have 5 different manufacturers that make these oil canisters, all that are actually able to fit your car. They're the exact size, shape, and threading so that we don't damage your car. That's why we have standards. If you want to go specialization, something like a Rolls Royce, which I'm 99% sure you cannot take to a express oil change anytime soon. Because you want to talk custom, that's custom. I'm trying to think of another big custom car, something like a Ferrari. Is that, huh? Aston Martin, Tesla. Those are the type of the really high-end cars that nobody can work on except for the dealer. Maybe. So that's what I'm saying, is that the whole reason we have these standards committee is so that on standard things, anybody can work on it. Anybody can get what they need. You can have more than one manufacturer of a product, and every manufacturer has to meet those specs. Does that make sense? So cylinder sizes. We have cylinder sizes that are to spec. So in other words, the bore, which we'll talk about later, the outer diameter of the cylinders, the inner diameter of the cylinders, all of that is standardized so that I can go to any manufacturer and say, I need a 2-inch cylinder with a 1-inch bore. And I need it to extend 3 inches. Well, sure, we got that on hand. And if I go to another manufacturer and say I need the exact same thing, well, sure, they got it on hand. And if I compare the two, you might have a little variance, but it's not going to be by much. That's the marvel of standardizing. Because if you really consider the fact that back in the day, standardization was not, customization was the big thing, right? Kind of like, well, back in the day, you had horses that were the engines, right? Well, the only one that could provide you with horseshoes was the farrier, right? That's the guy that would come out, trim the hoof, and put the shoe on. The shoes were custom to each horse. Nowadays, I can go buy a horseshoe, might have to heat it up and mold it a little bit, but otherwise, it fits. Kind of like a tire. I can go get a tire and it will fit. Why? Because it's standard. So having standardized cylinders, having standardized mounting styles, so creating better materials, improved designs, where practical standardization. This is the whole goal of a lot of these committees. Okay. Society for Testing and Materials. Excuse me. So these guys work for the information infrastructure and guide design, manufacturing, and trade in the global economy. So they create standards for technical standards for materials, products, systems, and services. Sorry. So the Society of Automotive Engineers, kind of sum this up for y'all. So these are the largest developer of technical standards for land, sea, air, and space industry. The industry, government, and public are using these designs for manufacturing, testing, quality control, and procurement. So like I said, all of this just kind of builds on the fact of we like standards. They make everything easier. You don't have, if you get a 3/4 inch bolt, you can get a 3/4 inch nut and it actually will fit. ANSI. Many of y'all have probably heard of ANSI before. What is ANSI?
I was close. American National Standards Institute.
Where have you heard of ANSI? They're part of robotics. Basically, ANSI is manufacturing. Okay. So standardization, believe it or not, is voluntary. You don't really get, you can have customization, but standardization is voluntary. So they're part of that. ISO, International Standards Organization. So I'm not going to try and get too technical with a lot of these. These guys do technical standards for the international market. So that's where the metric system starts coming in. So if you have a 3mm bolt, you can get a 3mm nut. And you can get that anywhere in the world. Doesn't matter if I'm in China, India, Japan, Africa, Asia, anywhere in Asia, or anywhere in the European Union. South America, North America, Australia. If they ever made it in Antarctica, you could get it in Antarctica. You know, Greenland, Iceland, anywhere you go, same standards, same thing. Makes things very convenient. All right, so 6:30. So we'll go ahead and take. So fluid power systems. So we have electrical, mechanical, and fluid as ways to transmit power. For most industrial, I will say about, I'd say almost 100% of most factories have some form of electricity. I would say also that about 90% of most factories probably have some form of fluid power. Hydraulic, pneumatic, some form. Pneumatic is probably one of the most common. Second common would be, you know, of course, hydraulic. The whole reason pneumatic would be common is because pneumatic is a very clean energy that is very easy to run, which also we'll see whenever we get to lab.
I mean, you know what I'm saying? It's like when they were doing like the backhoe or the equipment.
So no, hydraulics has a very specific way they're set up. And they have a very specific way they have to be piped and have to be cared for. And pneumatics has their own set. Now, could you technically make a pneumatic driven backhoe? Yes, technically you could. Would it be as strong as a hydraulic? No. Or if you wanted one as strong as a hydraulic, you would have to have much bigger pistons. Pneumatics, I'm trying to think about what the maximum pressure for pneumatics is. About 8, I'm sorry, most applications for those are about 80 to 100 psi. A lot of them will top out no more than about 120 versus 1 to 5,000 psi for hydraulics. That's why I keep saying hydraulics is a powerhouse. Hydraulics is the strong man. Pneumatics is more of the normal everyday person. Hydraulics are what you call on for the big jobs. Pneumatics is what you call on for most every other application. Because you don't need somebody that is, 300 pounds, 6 feet tall, muscles that you can't even wrap your arm around, your hand around, right? You can't even wrap both hands around. Their arms are like this. When we talk about, looks like Gaston off of Beauty and the Beast. Everybody remembers that one? That's hydraulics. Pneumatics is pretty much everybody else. That's why pneumatics is used more often, because pneumatics they're easier to use, and they also sometimes cost a little bit less. When it comes to fluid, think about how much oil costs. How much does oil cost today? What's a quart of oil? Getting up to be about $25, $30 a quart, if I'm right. Versus pneumatics, which is just air. So pneumatics, I would say, is used in probably about 80 to 90% of most applications. Hydraulics, though, they are the ones that you bring in whenever pneumatics can't do the job. And especially when electrics can't do the job, because electrics, let me put it to you this way. What happens if you stall an electric motor? Let's say you have a impact wrench that's pneumatic versus an impact wrench that's electric. And you get a bolt that is stubborn as heck and won't move. What would happen if you put the electric on it? You're gonna do what? What's gonna happen to that motor? It's gonna burn out. What about the pneumatic? But will the motor in the pneumatic be damaged? No, it won't actually. That's a really big difference between electric, hydraulic, and pneumatic. Hydraulic and pneumatic, I can stall that motor out all day long and it won't really damage it. Electric, yeah, you're gonna burn it out. So with a lot of applications, it depends on the application, but 90% I would say use some form of pneumatics, and they also can use hydraulics as well. But hydraulics is going to really depend upon what they need to have done. Y'all agree? Okay. So fluid power systems that use a liquid are called hydraulic, because they're using mineral oils or some form of oil. And of course, ones that use gas are called pneumatic. And this one is the most commonly used thing, is pneumatics. Again, it is safer because you can stall it out, you can use it in explosive environments, and really have very little issue with it. If you ever had to use a pneumatic air tool, those things are a beast, but they're a very safe and tame beast. So we use pneumatic systems a lot for tools, linear motions and rotating motions. We use a lot of cylinders with this. We use them in a lot of tools. All you have with a pneumatic tool is basically a pneumatic motor. And those things can be quite powerful. So some of the terms you definitely want to know here are force, area. So force is anything that changes or tends to change the state of rest. That goes back to, I think, one of Newton's principles: an object in motion stays in motion, an object at rest stays at rest, unless acted upon by a outside force. Okay? Area should sound familiar. You had to learn that in math, I think, back in the 5th grade. Yeah, they tend to reiterate it and beat it into your head. Never could figure out why. Then I became a teacher, and now I remember every bit of that. Weight, heaviness or mass, density, how closely set or crowded something is, mass, body of matter with bulk, size, expanse or massiveness. But the big three, I would say, are force, area, and pressure. You want to definitely memorize those names because we're going to be big into them. So pressure is the measure of intensity of a force exerted on a specified area. And here's the weird thing is that you have imperial measurements, which I think we're one of like the less than a handful of countries. Yeah, I think, yeah, there's like 3 countries, us, Liberia, and Myanmar that still use it. Myanmar, I don't know how to say it. So you're talking about a place in Africa and a place in uh, Asia, specifically around the Philippines and India. So 3 places left. We're a very lonely 3 places. Pressure. Pressure is another really big one. There's 3 are going to be part of a formula you will need to memorize. Well, and speaking of formulas, Miss Janice did go out to our Birmingham bookstore today, apparently, or yesterday, and she found that both books are still there. They are they 118, are under 118, INT 118? On the electric, it's not on the website. Yeah, I know. I don't know why they've not done that, but I wish we had our bookstore. I know. It's not, if it was up to me, we would still have our bookstore. But it is not up to me, so. But yes, we are one of 3 countries that still uses imperial. Everybody else uses metric. But everybody also has a way to convert, imperial to metric. They generally have, most gauges will have both, something that you can read. Kind of like on your car, it goes kilometers. I cannot talk right now. It goes kilometers and miles in your car. It goes mph and kmh. So units, US customary system, it's based on yard, pound, gallon, bushel. I didn't really have to look it up because it's only used in USA, Myanmar, and Liberia. So us, a little place in a little country in Africa, and a little country in that right next to India. We're very special people. You have the imperial standard, which is the British imperial, which is very similar to ours, and they still somewhat use it, but they are also converted to metric. So we're one of the last big superpowers still holding the line. Everybody else switched a while back. But the international system is the scientific. It's based on the meter, kilogram, second, ampere, Kelvin, candela, and mole. Used in like 99% of the world. Well, since there's 3, 4 countries, maybe 98%. Hmm. There's a lot of places, and we actually did try and convert back in the 60s and 70s, I believe. It just didn't take. We're all just too stubborn to move, so.
This will probably be easy for them. They ask me for help. It's like, I don't understand none of this.
Well, they need to do it because the metric system is all powers of 10. You don't have to memorize anything dumb, like how many feet are in a mile? Well, it'd be a power of 10. But here it's 5,280.
Yes, I keep wondering exactly who came up with the imperial measurements because they're just insane. Britain. Yeah, I know we inherited it. But at the same time, who came up with it in Britain? Who came up with it in Europe that you have you have this many pounds in, this many ounces in a pound or this many ounces in just, it's all a little bit weird. You have to ask yourself, who in their right mind came up with this? Like they say, the foot, 12 inches, is based off somebody's foot. My question then goes to, well, if it's based off somebody's foot, how did we find 12 inches in that foot? How did we determine an inch? Why did we divide it by 12? There's just so many questions I have about the imperial system because you just sit there and ask yourself, who psychosis came up with this? Kind of like fathom, okay? Bushels. Who in their right mind?
Who sat there and thought about milliseconds? I mean, seconds are, but what were you doing that day? You just
You have to wonder who came up with these and if they were just bored one day. Anybody else have a theory on it besides boredom? Well, actually, the kite thing is a total lie. Let's put it this way. If he actually pulled that off, he'd be dead. If he actually tried to pull off the kite thing, he'd be dead. How many volts and how much current in that lightning? Give or take 50,000 volts, and we won't even talk about how much current goes through a lightning strike. No, you'd be a crispy critter in an instant. I'm sorry, you're not going to live through it. Not to mention, how would you get a kite to fly in a rainstorm?
But it wasn't in Alabama.
You know that. It wasn't called Alabama until the 1800s.
Okay, so 1819, but still, it was somewhere in Massachusetts.
Okay, back on target. Collective ADD. Let's take that and get back to what we're doing. So pressure, this is the amount of force exerted on an object divided by the area. So we have atmospheric, gauge. So atmospheric. Anybody know what atmospheric pressure is at sea level? What is 1 atmosphere? 1 atmosphere is 14.7 psi. So at sea level, you have 14.7 psi holding you to the earth. Okay? So then you have gauge. Now, gauge pressure versus atmospheric. Gauge pressure generally compensates the atmospheric. So if you're reading gauge pressure, basically they've subtracted 14.7 psi off the pressure. And don't ask me where somebody came up with 14.7. I really don't know.
Is that a formula?
Yes, you probably want to write this down, especially the difference between atmospheric and gauge. Below atmospheric pressure is it considered a vacuum or negative pressure. In other words, that's what you create whenever you stick a straw in a drink and start sucking the liquid up into your mouth. You create a vacuum because you're removing pressure. So thus, the way that works is that the pressure on the liquid outside the straw becomes less than the pressure on the liquid inside the straw. That's what actually causes that, believe it or not. So one standard atmospheric pressure is 14.7 psi-A. So psi-A is atmospheric pressure. So psi-G would be compensating that. So you might want to make a note of that. There are questions on tests that come up with that. You also have 101.325 kilopascals. Absolute pressure is, I'm sorry, you have to add the 14.7. I'm sorry, that's kilopascals absolute. Trying to read this too fast. So you have 101.325 kilopascals absolute, 29.92 inches in mercury, or 760 millimeters in mercury. That's what the Hg stands for. Yep. And I don't know if this is probably going to come up on my side, not y'all's. I'm just going to try and pull that. Yeah, I'll pull that over real quick. But yeah, there is a distinct correlation between temperature and pressure. So. So that is, no, it's not below sea level. It's below atmospheric pressure. So let's say you're using your vacuum cleaner at home. That sucking motion is created by creating that vacuum. It's pulling in negative air pressure. Does that make sense? Like I said, back to the straw thing, when you are basically putting a vacuum on that straw. Think about, have you ever done this where you suck the liquid up into the straw, you cap it off at the top with your finger, and you're actually able to lift the straw out of the glass and the liquid is stuck there. It's stuck there because the pressure that is inside the straw is less than the pressure outside the straw, which is what holds it in there. So that's what it means by below atmospheric. Because I'll tell you right now, anything below sea level is heavier. The deeper you go in the ocean, the more pressure you actually experience. And that is, the closer you get to the Earth's core, the more pressure you experience. The deepest place in the ocean is the Marianas Trench. And I cannot remember how, I think it's like 2 miles deep, if not more. Yeah, it's deep, deep. The deepest place in the world. And the pressure there would be enough to basically turn you into a molecule. You would not survive outside of a submarine. Yeah. Humbling to think about. but the deeper you go, the more pressure your body experiences. This is kind of the problem that a lot of people in mines face, is the deeper they go in the mine, the more pressure they can experience, the harder it is for them to work. And they also face a whole lot of other challenges, including the fact that they're working in a very dusty, dirty environment, and they end up with black lung fairly frequently because they suck in so much particulate every day. But I digress. Yes, I can get off topic easily. I'm sorry. So pressure units, you have PSI, which is the most common one here in the US. That is standing for pounds per square inch. So that is quite literally the way you say 1 pound of force exerted on an area 1 inch squared. So in other words, at sea level, you're experiencing 14 pounds constantly, or I'm sorry, 14, almost 15 pounds per square inch of your body that is holding you at sea level. Which sea level means like basically sea level if you go to the beach. Now, I won't get into the other part of that. So then you have pascals. This is the scientific unit of pressure. So this is 1 Newton exerted on an area of 1 meter squared. So 1 Newton is the equivalent of mass, essentially is what they're calling that. So then you have kilogram force per square centimeter, or 1 kilopascal, which is equivalent to 0.145 psi. You have bar, which is 1,000 kilopascals, which is 14.5 psi. So essentially, we experience 1 bar of pressure, or 1 or 14.7 psi at sea level. So we experience 1 bar of pressure, roughly. You have inches of water. You have inches of mercury. Again, that's where the Hg comes in. The Hg is mercury, so that means vacuum. One of the coolest experiments I've ever seen done with a vacuum. I have to say I was a big Mythbusters fan, so I will go ahead and wax poetic on this. One of the last episodes they did, they took a car, made 3 boxes with silicone gaskets, and used a shop vac to lift a car. And one of the things they talk about is how much of a vacuum they're drawing. And you measure a vacuum in either inches or millimeters of mercury. Where that came from, I do not know. Why you would use quicksilver for anything, I could not tell you. It's always seemed a little weird to me that we use something that is completely deadly to do anything with, but hey. No, this actually is used worldwide, hon. So you definitely want to know the difference between PSI is probably the biggest one we'll use in this class, but the other ones you might see is passing. But yeah. And by the way, if you ever look up that episode, it is one of the coolest episodes. Because at the very end, they unplugged the vacuum cleaner to turn it off, and the car just drops. Well, they just can't build enough of the fan base is too loyal to the other ones. To the old ones. They don't like the new ones. All right, so this is a conversion table. This is pretty standard. You can find this online. Like I said, the main one we'll be using is the PSI. Knowing that a vacuum is generally used with I need to slow down and actually talk. A vacuum is associated in either inches of mercury or millimeters of mercury, is something you might want to keep in mind. It's a great test question, or just, a great Jeopardy question if you ever get around to doing something like that. I digress. But this is what you would see most pressure gauges as. The ones in the US typically are PSI. You might see one in bar, but if you look, it also tells you kilopascal. I'm sorry, bring my mouse over. Hey. So this one's in bar, but you can also see kilopascals. Or it says that's how you convert it to kilopascals, and it does PSI on the inside. This one's for a vacuum. You can see it's in inches of mercury for the black gauge, and then bar as well. This one is kilograms per centimeter squared versus PSI, which is the one on the outside. So gauges will generally come more than one way, just like your speedometer on your car, right? Mm-hmm. Which one you're looking for and which one you're looking at. And generally it'll try and give you a little helpful hints, like it'll have, this one's being for, if it's red, it's one thing, if it's black, it's the other. That's pretty typical of most dials, especially anything that's used across borders or used by multicultural, multinational corporations. So someplace like Broza or Mercedes, which Mercedes is, I believe, German. No, I think it was originally French. Might be wrong. I can't remember anymore. Hmm?
I was going to ask you about that. Go ahead. No,
Okay, so this is your digital blood pressure monitor. So it's given in millimeters of mercury, which is able to convert into PSI. That has a lot to do with the electronics on the inside. So you have systolic and diastolic. Don't make me try and say the big words. I can't say them tonight. Diastolic, thank you. But they are measured in millimeters of mercury. I don't know why they measure it that way. I just know it is. That is something you'd have to ask somebody in medical as to why they measure it that way. So unit of force, this is, again, we go back to Newton's first law. Anything in motion or out of motion will stay the same state unless acted upon by outside forces. We use pound force in imperial. The people everywhere else in the world use the Newton. Sorry, the Newton. I guess they named it after Sir Isaac Newton, who Newton's first law. I think that's Newton's first law, isn't it? Yeah, first law. Thank you. I have. No, my brain just misfires every now and then. So work and power. For anybody who's taken intro to electrical engineering, you know work and power are hand in hand. Well, anytime you've done work, you have to use you consume. I'm going to stop trying to say that now. So work is done when force is moved some distance. So basically, if something's not moving or something's not being used, you're not getting any work done. Right? For electricity, how do we know its work is being done? Because a state has changed, right? The motor is on, the light is on, something has changed. Something is being created, destroyed, something, right? Well, same thing with this. we're making something move some form of distance. So in this case, we're doing force times distance, and it is measured in foot-pounds or inch-pounds. And power is how much work was done in a given amount of time. So if we go back again to electrical engineering, power is how much work did it do over X amount of time, right? How much light did you consume, or how much wattage did you consume, right? So force times distance, or work divided by time, force times speed, something along those lines are what you're going to be using for that. It's not, they're good formulas to know. So to keep that in mind. So here's a couple of broken down formulas for you. So work is force times distance. You have velocity, which we really don't use a lot of in this class. That's distance over time. So how fast do you drive your car? Well, that's the velocity of your car, right? Some of us drive like speed demons, some of us don't. So then you have power, that's work divided by time, and then you have power, which is force times velocity. Time has a big factor in a lot of things, right? So the biggest law here is Pascal's law. That is, pressure exerted on a fluid is transmitted in all directions and acts at right angles to the containing surfaces. In other words, the more you put pressure on something, the more it tries to move out. Okay, does that make sense? So you might want to write this law down. It is very important to everything we talk about with a lot of this. Or at least know something of it. And that is that, so this is why you have to check your hoses very frequently. This is why hoses can wear down from the inside. Have any of you ever used a sand blaster? Well, the tips of a sand blaster, what happened to them very quickly while you use them? They tear down, right? That is a quicker version of what fluids do to hoses. Because when you confine a fluid and pressurize it, essentially what you're doing, so here's your hose. You're putting your fluid down here and you're pressurizing it because it's got something to do down here. That fluid is pressing not just down, but into the walls of your pipe. That is what Pascal's law tells us. And over time, that's what causes the erosion that causes breakdown. Does that make sense? That is what causes the erosion that causes a breakdown in your pipe systems. That's why the hoses in your car have to be replaced periodically. Not because the outside coating sometimes, it's because the inside coating. Eventually it all just doesn't work anymore. Okay, so let's say my shower head is down here, or the top of my garden hose. Whenever I don't release the pressure, and the pressure just stays back here and builds, what does it start looking for? It starts looking for that little weak point right there. Right? That one little weak point that it can sit there and exploit. Because the second it can, it's going to hit that weak point and it's going to try and get through it. That's how you end up with leaks. That's why if you've ever had a garden hose for longer than, let's say, a week, what happens to it every time? There's always a big leak at either end, right? The seals on it, they might say that this thing does not leak. They will never say it does not leak. Why? Because it will always leak at the seal. The seals are not sealed. That and it's water, and water is less thick and viscous than oils that we use for everything else. Not to mention water tends to cause carry contaminants, right? What do we have a lot of as far as contaminants in our city water supplies? I was thinking more limestone particles because we have hard water, right? Calcium, lime, and rust. We have a lot of calcium that gets carried in our water supplies all across Alabama. Those kind of mini particulates, that's going to start really wearing down the lining of these. And that's where you end up with all your leaks. That's why you got to change hoses and piping occasionally because it just wears out. You know, the pipes behind your walls, how you have to, it's not often you have to change them. Most piping is good for at least 50 plus years most of the time, depending on if it's metal or plastic. It always depends on that. But eventually, it starts to wear and break down from all of that. The other thing that can happen with it is what? It starts to build that skin of calcium. Yeah, if you've ever seen a shower head after about 20 years of use, it's all but useless until you dip it in some CLR and break it down. But in your pipes, that's happening as well. My dad and I had to take out a hot water heater from our basement. And just out of curiosity and trying to figure out if we could even fix it, we decided to cut it open. This thing was caked with calcium, like an inch or 2 inches thick. I am not kidding. This thing was like, and the whole thing of it, the entire interior of this hot water heater was caked with calcium. Simply because all the calcium we have in our water supplies, it builds up. And in a hot water tank, it actually has a chance to settle. So that is Pascal's law, is that it's going to try and hit those right angles. It's going to put pressure and it will, over time, cause breakdown. It's also why you don't see square pipe. Not a lot of it anyway. So confined fluids, the more you pressurize it, the more it pushes back. Okay? That's why a fluid likes to have a place to go. If you over pressurize it, you're gonna break seals. You're gonna end up having other issues besides blowing your piston. Not even if you put too much pressurize on it. Have any of you ever done the bottle rocket? Then you know exactly what will happen to that piston if you put too much pressure on it. The second it can, it's going to go boom. It's going to launch. So this should look semi-familiar. Force, area, pressure. So force, if I'm looking for it, I multiply area times pressure. If I'm looking for pressure, I divide force by area. If I'm looking for area, I divide force by pressure. Okay? You might want to have this. Yeah, it should look very familiar to Ohm's law. Yep. I was gonna let y'all borrow these real quick for the night. Let's see, I've got, I had more. Huh, I do not. I'm gonna let y'all borrow these for just tonight. So y'all can kind of be looking through them. Because the fact of the matter is, I've probably dog-eared every single one of these so that I can find my pages really fast. So very towards the front, I think it's like page, right here on page 9. So page 9, you should see, this is why you want this book. This is your cheat sheet for every test. Because you should see at the very top, I'm sorry, not the very top, it should be,
Towards the bottom of the column.
yeah, here we go. Force is equal to area times pressure. So third one from the bottom. On the left-hand side of that page. Force is equal to area times pressure. That's one that you definitely want to have earmarked for this because that's one that's going to come up frequently. Okay. Force is equal to area times pressure. That's one that's going to come up quite frequently. So this is the matching units. Again, the ones I'll pretty much require for y'all are the pounds per square inch, PSI. But it is good to be aware of the other ones. So you have newtons that equal into pascals. You have newtons that also equal into megapascals. How does that work? Newtons times millimeters squared versus newton. I think somebody got those backwards. Because meters squared times the newtons should be megapascals, not the other way around. I'll have to double check that one. I did not write this one, so I probably need to correct that. I think that one's backwards. But anyway. So again, Pascal's law, the more pressure you put on it, the more pressure it's putting on the outside of its container. So let's say I have a bottle of water here. The more pressure I put on it, the more pressure it's putting on its walls, right? That's Pascal's law. Okay? I have nothing but air in here, but the more I press on this air, the more it's pushing back against it. And not only pushing back, it's pushing at the sides of its container. Okay? You'll see how that kind of works? So that's why that works. Force multiplication, because Pascal's law, pressure in one place is used elsewhere, and it allows the force to be multiplied through use of surface areas. So again, this kind of goes back to why does a jack work the way it does? Why is it that every 5 times I move a jack, I can get maybe an inch on the other side of it? Well, because the piston in the jack that's driving the pressure into the other piston that's pushing up is transferred. It's a transference of force. Does that make sense? So for this particular one, we have a 1 Newton square area and a 5 Newton square area. What this essentially means is that for every 1, instead of newtons, let's call it inches. For every inch I move one piston, I'm going to move 1/5 of an inch on the other one. Does that make sense? So for every 1 inch I move here, I move 1/5 of an inch over there. If I want to move a whole inch on the 5 side, I have to move 5 inches here. So in other words, here's my side of the jack. Here's the side of the jack that's supposed to lift my car. I have to pump this side 5 times to get one side of this, get 1 inch out of this. Does that make sense? I have to work 5 times harder on this side than I have to do on that side. But the pressure transfers and allows me to lift that other side. Does that make sense? Okay, so work out is equal to work in, power out is power in. The output forces are greater than the input force, but only because the pressure in one is transferred to the other. So in other words, if I have, let's say I have 500 psi here, when I press on this, 500 psi is transferred all the way across. That's the great thing about fluid power. So if force goes up, distance goes down, and speed goes down. We'll see some more of that as we go. So for this particular one, we're given area, we are given the force. So if I have force is equal to area times pressure, okay? I have my area and I have my force. I'm looking for my pressure. So that I'm going to use force divided by area equals my pressure. So 100 pounds divided by 10. Yeah, in this case, you don't really have to worry about the units. So 100 divided by 10, I'm going to end up with 10 psi, yes? Ten psi. That 10 psi comes all the way over here to the other side. So I end up with 50 inches squared, or 50 times 10. So my total force out is 500. I end up with only 100 pounds. I can lift 500 on the other side. Does that make kind of sense to y'all? All right, so if pressure is equal to area divided by force, 100 divided by 10 is 10 psi. So the only bad thing is that my output speed is going to be very slow, right? It goes back to the car jack. Every time I press that lever, I'm not going very fast on the other side, am I? How long does it take to jack up a car? At least, right? Because you're having to sit there and do all this work. It doesn't matter how fast or how slow you go. It's not going to move the other side any faster, really, right? It's going to move at its own pace. So the fact of the matter is, I can be pressing with all my might here on this 10, using 100 pounds, but I'm only going to get 1/5 the speed on the other end because it is 5 times bigger than the other piston. You are having to move the smaller piston, you're having to move it 5 times for every one time you move the other one. Does that make sense? So speed and distance will be 1/5 of its counterpart. Does it make sense? All right, so before we get into this one, there it is. So we cannot just take the size of the bore, which is this area right here. We cannot just take that and use it. We have to find the area of the bore because we need the inches to say inches squared. It cannot say inches squared until we find the area. Now, the easiest formula I have ever found for area is where you take the radius, you square it, and you times it by 0.707, I believe. That is the fastest way to find area. You don't have to worry about pi. It's just times 0.707. Okay. You can do pi r squared, but I think the formula that leads to this particular one is the where you use diameter. So that is where you divide it by 4. Where you do pi times diameter squared divided by 4, you just take that out and you just, one of those books has that formula. I'm trying to remember exactly which one it is. Is it the radius or the diameter? I've got it written at the top of the formula page. Somewhere. In one of these books. Yes, it's diameter squared times 0.785. Excuse me, I'm sorry. I'm wrong. I'll admit I'm wrong. Formula I'm looking for is d squared times 0.785. Diameter, yes. Then you don't have to find the radius. So diameter squared times 0.785. So the first one would be plugging this in, 3 squared times 0.785. So what does that give you if you plug it into your calculator? Oh, and here's another nifty thing about the book. If you flip forward a couple of pages where it starts giving you air pressures, I think that's about page 16. It actually gives you most of the bores and their areas right next to them. And write it up here. So what you should have ended up with is 7.065. And I believe it is page 16 where you start to see the pressures with PSIs in it. And then if you look right next to it where it starts listing the bore sizes. To the far left of the page, Right next to it, it says rod inches and then effective areas in square inches.
So that would be the bore?
Yes. The dark ones are where you have the actual area of the bore. The dark ones are where you have the actual area of the bore. And then it shows you the common rod sizes. So the rod, this section right here, this is the bore. That's what we concern ourselves with. So is it fairly close to 7.065? Pretty close. So we have our size of our bore and we have our pounds. So what's the next thing we need to find before we can even think about going to the other side? We found our area, we have our force, now we need our pressure. So we take 200 and divide it by 7.065. What is my pressure? Let's round to the first place behind the decimal. All right, next we need to come over to this other bore and we need its diameter. So what is my diameter at a 5-inch bore? You can do 19.6. I'll extend out to 19.625. What does the little book say? 35. So pretty close, right? So now we have our diameter here, we have our PSI, multiply those together and we should get our force. What is my force on this side? Let's round to the first place behind the decimal. So we're looking for force out. Not 0.3, because if yours is looking at mine, it's 555.3875. So rounding to the point behind the decimal should give you 555.4. Be careful when you're rounding and try and make sure you round up when it's appropriate, because that right there will actually hit you on a test. You multiply your area, so you multiply this guy times your pressure, because your pressure is not going to change in your system. Why? It's a closed system, right? You can't compress it. So force in one side, you're going to get force multiplication out the other. Does that make sense? So in order to solve this one, you had to solve for area on both sides. You had to find your pressure before you could find your force out. Diameter's not, you use diameter squared times 0.785. Yes, that is a constant formula for area. And believe it or not, when you've asked Google about it, it doesn't have it. I don't know why. It just doesn't like that particular formula, but it's actually a very fast and efficient formula. What they did was divide pi by 4. I think is how they did that. So yeah, it ends up being 0.7853981316334, so on and so forth. So the fast answer to that is 0.785. So it's quite literally your diameter squared times the quarter, the 1/4 of pi. Which is a very short way around doing all this. No extra work required. You don't have to try and divide, well, 3 inches is, everybody knows that's 1.5, but, if you end up with this weird number, you'll end up having to try and divide that in half times pi and everything else. You can just take the diameter as it's given, multiply it by, square it and multiply it by 0.785. Yep, this formula right here. I would definitely write that down. That is a really great formula to have. Yes. Yes. So you multiply 19.625. This is the 5-inch bore. That's where you divide 200 by 7.065. You have to have PSI for one side or the other. I'm sorry. I didn't mean to lose you there. So you have to find the area of one side. You have to have the area, period. If you don't have the area, you don't have the ability to finish solving any of it. So once you have the area of both bores, you have force on one side of some sort that you can use to find pressure. Once you find your pressure, you can take the area of the other side of the equation, since the pressure is not going to diminish, and use it to find the force out. Does that make sense? This one had several steps to it. Mm-hmm. Mm-hmm.
Area is the diameter of the bottle. The 3 and 4, that area right there,
Mm-hmm.
that's the diameter.
That's the diameter, yes.
That's divided.
That's where you square 3 and multiply it by 0.785. In order to get your area for your bore, you took 3 inches squared, so basically 9 times 0.785 to get 7.065. Then once you divide 200 by the 7.065, you get 28.3 psi. The area of the 5-inch bore. Next. Maybe this will help a little bit better. So to find area 1, we took 3 squared times 0.785. 0.785 is pi divided by 4. Okay? So once we found area 1, we had to find the pressure of the system overall. We know 200 psi is being put on one side. We already know the area of that one side. So then we just find the system pressure. Does that make sense so far? That's where we ended up with the 28.3. Then we found the second area. That's that 5-inch bore. We did that again by taking our diameter, which is the size of the bore, square that, and multiply it by 0.785 to get the 19.625 inches squared. Okay? Then to find the second force, we take our area and multiply it by our pressure. So we have our, find my little dot dot. There's our pressure, there's our area. Okay, so area, pressure, we get 555. I think we ended up being 0.4, but close enough-ish. Does that make a little more sense? Don't worry about the second one down here. I'm not really, that's just another way of finding it. Stick to the way I was showing you. It's a lot simpler. It's kind of like whenever you're trying to find all the answers for a circuit. Yes, there are shortcuts you can take, but sometimes just the direct 1, 2, 3 steps, a lot easier and a lot less of a headache. So in this case, we literally did, see if I can do this. Let me get a different color here. Excuse me. 1, 2, 3, 4. Does that make a little more sense?
Why are you writing the steps?
Those are the steps.
Okay.
Step 1, area 1. Step 2, pressure. Step 3, area 2. Step 4, force. Okay? I got the pressure by dividing force by area. Yes. Pressure is directly transferred. Put that out there too. Like I said, d squared times 0.785 is probably the fastest, easiest way to find area that I've yet to come across. Actually, it makes me wonder why no math teachers teach it, and Google doesn't even know it. What do you mean?
If you did it like 5 squared times 0.785 and work it the other way, would you come back out with 200 on?
Yes. It might be a decimal or two off, but you should end up with roughly 200. Remember, you're actually not dealing with straight numbers, you're dealing with a lot of decimals. So anytime you deal with decimals, it's never exact. It's kind of like if you truly think about it and start looking at formulas like if you add 2/3, which is 0.6 repeating, never ending, to 1/3. Now mentally you know that's a whole because 1, 2, 3 all together. But mathematically, 6 plus 3 is 9. 6 plus 3 will never equal 10. The only way you get that is by rounding. So same thing here. It's all decimals. Whenever you're doing any kind of decimal work, that's exactly what happens every time, is that it's never exact. You will get close, but the more times you do it, the less accurate it is. Okay? That's just par for the course of anything to do with decimals. Like that is my favorite example to use because it truly makes no sense unless you round it. 0.6 repeating plus 0.3 repeating is just 0.9 repeating. The only way you can get 1 is by rounding at some point, which would set off the chain reaction and end up being 1. So decimals are funny that way. You think they're most exact thing on earth, they're not. All right, so for Pascal's law, pressure on the 1 inch squared area is transferred equally throughout the system. That's why your pressure in your house, well, I won't say it doesn't diminish because the more faucets you turn on, the more your pressure starts fizzing out. That's another thing for another time. But the pressure is transferred equally through the system. When there's only one valve open, you get the same pressure the entire time, right? So pressure on the 5 inches squared is 5 times greater. But the speed and distance of the piston is 1/5 that of the smaller one because the area is 1/5 of the larger one, right? Does that make sense? So in other words, if you were to put a car on one side and a truck that weighs 5 times its weight on the other side. Yes, for every 5 inches the car goes down, the truck will go up 1 inch. Does that make sense? But vice versa, if that truck is going down 1 inch, it's going to raise that car 5. Does that make sense? 1 and 5, 5 and 1. Does that make sense at all? So airflow in pipes. This is something that is very interesting, okay? So how many of you have ever been whitewater rafting or canoeing or fishing or been in a boat of some sort near water? Or just watched a stream of water? You know what I'm talking about then. Whenever the water is going down a straight and narrow channel, everything flows smoothly. It all just keeps going, right? There's nothing to divert it. Everything's just going in one smooth way. But whenever you put any kind of a bend in it, anytime it has to make a turn or a curve, what happens to the flow? It changes. It becomes turbulent, right? Whitewater rapids are notorious around very rocky areas. It changes how the flow works. Does that make sense? Well, the same happens in pipes. If you have just a straight length of pipe, flow is even, flow is great, nothing changes. It's what's called laminar flow. However, when you start putting bends in your pipe, putting 90s, elbows, T's, and everything else, that's when you get turbulent flow. Most of the time it doesn't affect much, but there are times where it does. Okay? That's the best way I can kind of give you an illustration of it that's visual. Most of the time we can't see air flow in pipes, right? You can't see air. unless you start putting smoke in it. If you've ever seen air, people do tests in aeronautics, whereby, I know one. Have you ever seen an air test on a car or on a big rig, a big truck, where it has that 90-degree drop off? The air going over it is smooth. The air behind it is just this swirling, chaotic mass that's just hanging out back there. It's all dead air. Does that make sense? Same thing happens in a pipe. Okay, it's all great and wonderful till you hit an obstacle, and then it's just like blah, and just all of a sudden starts coming apart at the seams. Does that make sense? I was getting a feeling of that. I didn't think he had actually gone outside. But does that make sense, guys? Like I said, air is not something you can see unless you start pouring smoke into it. That's kind of the odd thing about trying to prove any of this. But whenever they do tests on cars for aerodynamics, and they start putting all sorts of different colored smoke and stuff, and funny enough, whenever they're doing these kind of tests, there's two different ways they do it. They either will do it in an air tunnel with colored smoke, or they can do it in a water tunnel, because water acts the same way. That's why hydraulics and pneumatics work so well together as far as principles go, because they act the same way. If they have an obstacle that they have to get around, the flow becomes very turbulent around it. Kind of like if the rock is big enough in a river, the water just splits around it and goes behind it, right? But if the rock isn't big enough, the water that goes over it becomes very churned up behind it. Y'all know what I mean? Yes, I have been whitewater rafting. It's a lot of fun. Class 5 rapids are very interesting to look at. Even more fun to go down. I miss whitewater rafting. But whenever you're doing any kind of movement in water or in air, any obstacle creates turbulence. And that is what allows for turbulent flow. All right, so pressure, this occurs where there's resistance to fluid flow. So you have things like actuators, the orifice of the pipe, fluid through the pipe, hose and valves, anything that is making the flow stop. So just like in electricity, what creates work is you have to have something there that will do the work, right? Or something changes. Somehow, some way, something is changed in your system. That is what creates pressure. This is where you have the resistance. Does that make sense? I said, if I start jabbering too much, let me know if you need something clarified. Pressure required to move a load must be higher than the pressure required to support it. So an object at rest stays at rest unless acted upon by a different force. So in other words, if two people that are the same size lock hands and have pressure against each other, who's going to move first? Nobody. Or think tug of war. If both sides are completely equal, which side is the rope going to go on? Neither. You have to have something create a difference. You have to deal with friction, because friction is probably the worst thing in the world, right? Excuse me. Back pressure, I'll actually show y'all in lab when we get to it what back pressure is. But essentially, back pressure just means that the pressure on the front end can't move the pressure on the back end. So it gets back to that, if me and another person are the exact same size, everything, and we're pushing against each other, Neither of us is going to move until one of us weakens the other. Or one of us has a friend come up and can help us push. Right? That's back pressure. In other words, the pressure on the other end isn't being relieved, so thus I'm stuck holding this pressure here because if I let go, I'm going backwards. Does that make sense? Okay. You also can have energy that is acceleration energy. If you're having to move a load at a certain speed, you have to overcome the energy required to accelerate that load up to speed. So think about your car. What does it take to accelerate? Pressure on the gas pedal, right? But it takes a minute to move that, doesn't it? If you're at a red light and you absolutely slam your foot on that gas, is your car just going to take off? Anybody ever done that? Huh? No, what you have to do is bring it up to speed. Generally, you cannot just absolutely slam your foot on that gas and hold it there. What you have to do is kind of gently almost bring it up to speed, because otherwise you really are going to really screw up your engine. You could. It's going to dump a lot of gas in the, you got to ruin your engine for sure. You'll burn out your engine trying to do that. So what you have to do is accelerate slowly up to speed to where you want to be, because otherwise you are really, really going to have an issue with your engine later down the road, if not immediately, aka blow the head gasket. Really not a good idea to do that. I've known a few people that have done that. It's expensive. If you start tearing up any part of your engine on the inside, you are really going to have a bad day. That particular repair is, nobody wants that repair. That is an expensive repair. Huh? You gotta scrap your engine. You have to get a new transmission too, probably, because your transmission will fry too. All right, so flow, area, and velocity all have the same kind of thing. You don't really have to have this formula. Again, it is in the book, but this isn't one we generally use a lot of. So flow rate into a cylinder in cubic inches per second. You have area that's always in inches squared, and velocity of the piston moving in feet per second. Very self-explanatory here. This is the flow rate as how, gather my thoughts here for a second and stop trying to, I love it when I can't come up with a way to say anything. So this is all how fast is that cylinder moving versus what is the flow into the cylinder. So it's like whenever you're in your shower. If you want a high amount of flow rate, you make sure that nothing else is on, first of all. But your flow rate, I don't know how many of you have ever actually had to deal with this, because this is something that's happened in the last 10 to 15 years, I believe. They've put the water constrictors in every shower head that you buy. They're these little plastic caps that they stick down in a shower head that restrict the amount of flow that the head will have out. It basically causes it to drip instead of to actually pour the water out of it. So what you have to do in order to create a better flow rate for this, to be able to open up the whole shower head for use, is you have to pull the constrictor out. And like I said, it looks almost like a thimble. It is that small. It's just this little thimble-sized piece of plastic that's all got holes all in it, and it restricts the flow into the shower head itself. So it slows down that flow rate. because it restricts the area that's being used. Huh? So you actually have that problem going right now, huh? Yeah, let me see if I can pull y'all a picture of this thing up, because it's probably one of the most annoying things that you'll find. Yeah. So these are flow restrictors. Their job is to do exactly what they're called, and that's restrict the flow and the amount of water that is allowed into the shower head. They almost look like a filter sometimes, but they are not. They just restrict how much flow is allowed to come out of the head. So you go from a actual flow to a drip. And these are installed in all of them. And all you really need is a screwdriver or something, and you can actually pull these suckers out pretty easy. That's one of the most common ones right there. See, it looks exactly like I said, like almost like a thimble. And it's about the size of a thimble, but it's got little holes all in it, and it just keeps the flow rate down. Drives consumers crazy. I worked retail for years. I had more than one shower head returned to me going, "This doesn't work." Did you remove the constrictor? What is that? Asked and answered. All right, so these are the different units that we use with these. Again, you don't really have to worry about this a lot, guys. I'm not going to really be testing you on this. Force, that is one you probably need to know here. It's the capacity to do work or cause physical change. It changes the state of motion or rest in something. Generally, this is gravity. One of the funniest examples I can think of, well, not funny truly, but just weird examples I can think of. Where I lived in one of the neighborhoods I lived in, we had this really nice sized hill. Somebody didn't put the parking brake on their car. Their car ended up in one of my neighbor's houses, like actually going through the brick wall. Gravity is a very interesting force. Or I can think of another example of that same neighborhood. The houses behind us, somebody didn't put their parking brake on and their car ended up in the lake. That's one of those, oops. That's why I set my parking brake every time I park. Yeah, if your transmission ever slips, yeah, you want to put a parking brake on that. Yep. Always turn your wheels into where the curb is. Most people don't think about doing that anymore. I think that's a Ford. They like to have all those little weird gadgets, like weird tailgates and stuff like that. Ford has all sorts of weird, kind of like they can have a camera that backs up your truck. They have a truck that actually backs itself up so you can hitch up a trailer. Or Ram, yeah. Yeah, so there's all sorts of weird stuff out there that does weird things, but yep. The only thing is, that's actually a really bad thing. That can lead to bad things down the road. It's one of those things of, you see all these shows where they're talking about these self-driving cars, and I'm going, no. Yeah, I mean, airplanes are I love a backup camera. I will say that.
I do.
They're helpful, they make sense, but I'm so used to just looking behind me and worry about it.
I just do all that. Don't say I can sit back there and feel something. I'm just doing.
I will say this, I don't like a self-driving car. I don't like self-driving cars for one really big reason. People are very stupid with them right now. The technology is not completely proven. It's not completely there yet. I've heard too many stories of people that take their self-driving car, they set it on the course home, and instead of staying behind the wheel and paying attention and making sure everything's good, no, they go climb in the seat or in the back seat beside them.
Me and my mom and my sister got into an argument saying that Tesla was bad. And they were like, oh, Tesla's cool. No, it's cool for dumb people, but we all have common sense. Why would y'all want a Tesla? It's stupid.
Well, I mean, the technology truly has not been completely proven at this point. It is very much in its infancy. Tesla has actually had to go back and say our cars are not self-driving, they have driver assist. They had to reinvent how they said that because they were getting sued left, right, and center because you're a self-driving car and I can't make it drive me home. I can't go get party drunk with my friends and go have my car drive me home. Well, no, it's not that. GPS isn't even that accurate these days. I mean, seriously. Not to mention, anybody who's ever taken a sensors class, how accurate and how perfect are sensors at this stage? They're not. You have to replace them frequently. One sensor that's frequently replaced in cars, anybody know what it is? One of the most frequently replaced sensors. No, but that one is one. Your tire pressure sensor. That's the most common one that goes out. It's also one of the most expensive ones. The whole thing is, the reason they have tire pressure sensors in your car is because if your car is low on air, your insurance can claim that it's your fault, not theirs, and they don't have to pay for your accident. Yep. So area, I think we all know what area is. We'll kind of skip over this, but these are, the last ones are formulas for area. And again, you should see the area is equal to d squared times 0.785. That's a really great one. If you decide to use pi, don't go past 3.14. I think pi, I don't think they have found the end of pi at this point. And I think they've probably gotten, I don't know how far they've gotten on pi these days. I think the last time I checked, it was like 700 digits or so. Oh, I'm sorry. 31 trillion digits is where they're at.
That's all I can give.
3.14159265359 is just what they will show you on a calculator. But they are down to out to 31 trillion digits. That's insane. That's one of those things of somebody's obsessed and somebody's being paid a lot of money. That or you are doing it in your spare time just because you are bored. Which with COVID, I could actually see somebody attempting to try and find the NFI. It's kind of like binge watching all of Netflix. All right, so pressure is the condition of being pushed. So you have gauge pressure, which starts at atmospheric pressure of 14.7, which is a gauge pressure of 0. So like I said, gauge pressure is compensated for area. I'm sorry. Gauge pressure is compensating for atmospheric pressure. Then you have absolute pressure, which starts at true 0. That's where you get the 14.7 back into where you're at. So at sea level, absolute pressure is 14.7. Gauge pressure is 0. And the higher the altitude, I believe the less the pressure is. Yeah. So at so yeah, the higher you go, the less pressure there is. That's why for whenever you fly, they have to pressurize the cabin because the higher you go, the less pressure there is. That's why you can experience decompression at high altitude. And that's where they sit there and they drop those air masks, and you have to put the mask over your face and the person next to you if they can't do it. It's also why they had the original planes were not pressurized, so thus whenever pilots went up, they could actually suffer from pressure sickness. Because not only is the air thinner up there, but the pressure is thinner, and that really can mess with how your head does. Well, there's that. But even if they had oxygen tanks with them, the lack of pressure can do very funny things to the human body.
Flying or whatever in the air. I mean,
That tends to stem more from the fact that kind of like motion sickness in a car. In a car, the reason you get motion sickness is because your body is sending signals to your brain that your body is still, but your brain is receiving constant input in the signals that say we're moving. Because visually, your brain is sitting there going, "Oh, we're moving. This is where things are moving around me." Your body's sending the conflict of signals is what makes you sick. Okay, because your body's giving signals like from your inner ear and things, and that can cause that too. And the differential pressures and stuff when you go up and down hills, that all leads to motion sickness. That's why whenever I'm traveling with any of my nieces and they get motion sick real easy, I typically will crack the window just because that way your body is actually feeling stimulated by the air moving over your face and says, okay, so we are moving. It's only whenever you're in a sealed cabin and your body and your brain start that conflict, that's when people really start getting sick. Or at least that's the theories I've heard. I will go ahead and face that. I am not a doctor. That's the theories I've heard. So cylinders, the bore is what is moving, the rod is what moves the other end of it. The bore is what we put pressure on to move a rod back, the bore is what we put pressure on to move it back and forward through the system. Okay. There's two different areas we use to calculate this because we have what's called the rod. The rod is typically connected to something else that's doing work. So think about this like a piston on a steam engine. Everybody's seen the westerns where they have the giant steam engine pistons that turn the wheel and everything else, right? That. The rod is what is moving in and out. what it's attached to is what's moving, right? Well, the bore is what moves that rod. So on the push side, you have a lot of area. But on the pull side, the retraction, that's where you have less area. Does that make sense? Because the air has to go around that rod. So essentially, it's like, it'd be like trying to play tug of war, whereby on one side I'm free to pull, but on the other side I've got my arms wrapped around a pole of some sort and I'm trying to hold on to that rope. I don't have as much area in my body to help try and pull back. Instead, I'm stuck with something I'm trying to pull around. Does that make sense? Kinda, sorta. Trying to think of how else to say it. I know. It's the difference between trying to push a wall whenever the wall is flat, or push something whenever an object is flat, versus trying to push something when there's something sticking right at you. There's much less area and force that you can push against. Does that make sense? So that's kind of what this is. That's how they calculate for this. The rod is generally right in the middle of right in the way. It takes up its own size of area, but since it's cylindrical, it's really hard for anything to act at a right angle to a cylinder. Does that make sense? Exactly. So push is the extend area where you're just pushing against the bore. Pull is when you have to deal with that rod that's sitting right in the middle of your bore. So if you have a 2.5 inch bore with a 1 inch rod, I'm sorry, here we go. So what is the extend and retract force of a cylinder with a 2.5 inch bore and a 1 inch rod with 750 psi of pressure? So first of all, we would need to find the area of the bore. So what is 2.5 inch bore? What's the area of that? We'll leave it at 4.9 inches squared. You got another 25 minutes of class. So a 1 inch rod would just be 0.785 inches squared. So what would be my extend force if I have 750 psi on that 4.9 inches squared? So if I take 4.9 and multiply that by 750, I should get what? Well, theirs is a little bit different. I don't know what calculations they used for this one, but they get 3682. So it's close, pretty close. So 3,600 pounds. Okay. Now, if I'm going to calculate for my retract force, I've got to take that 4.9 inches squared and subtract 0.785. So the actual area I'm working with to retract, is 4.115. inches squared. So taking that and multiplying that by 750, my rough area you subtract 7.85 from 4.9. So bore minus rod equals retract area. Does that make sense? Because the actual usable area I'm able to use is what's at the bore. Because the bore is flat generally, or has right angle. Okay? So that's why my usable space is at 4.115. Does that make sense? So when you multiply that by 750, your retract force has gone down from roughly 3,600 to 3,000 roughly. Again, it just kind of depends on where your multiplications have come through. How accurate that multiplication is kind of how that works. So does that make sense on how the extend force is less than the retract? All right, so like I said, I won't go too much into some of this. What we do want to know is horsepower. So for dealing with horsepower, how many of y'all actually know how they calculate for that? So for electric horsepower, it's power divided by 746. I don't know where they get that number. And yes, I've had people ask me that. But for hydraulic or pneumatic horsepower, you might want to write this down. You might want to kind of make a notation in your book or see if you can find the formula in your book, in your little cheat book, whenever you get it. And that is that horsepower is equal to the pressure multiplied by the gallons per minute or cubic feet per minute divided by 1714 and multiplied by the efficiency. Now, why do we need to multiply by the efficiency? Because the efficiency has a bit of a problem, right? There is no motor or engine that is 100% efficient, is there? Especially over time, the seals break down and things like that, right? So when it comes to this, we have to multiply by the efficiency to get the true horsepower of something that we're trying to work with. But 1 horsepower is equal to 500 foot-pounds per second. I don't know how they came up with that. I don't know what breed of horse they used for that. It's probably a draft horse that weighs over 1,000 pounds. I have always wondered how they actually came up with horsepower. Gallons per minute versus cubic feet per minute. So gallons per minute is referring to hydraulics, because hydraulics uses gallons per minute as how much of a output a pump has. Does that make sense? And then CFM is cubic feet per minute, and that is referring to pneumatics because that is the volume of how much a compressor will put out. Does that make sense? Gallons per minute.
Divided by, and then in parentheses, 1714 times 0.85, close parentheses.
Mm-hmm.
So I was trying to see what is that way, or am I looking at the right one?
0.85, the decimal point is probably a standard that they use for efficiency, but the actual efficiency is generally given on most motors. That's why it says times efficiency. Not to mention efficiency is generally calculated by the fact of how much by age. So think about any motor that or any vehicle you've had to drive, the efficiency goes down as it ages. Because the seals break down and everything else by over time, right? Where things get gunked up. So the efficiency goes down over time. So, standard efficiency is great, but it is what it is. Excuse me. Bernoulli's principle, you have an increase of speed in a fluid that is you have an increase in speed of a fluid that occurs simultaneously with a decrease in pressure or a decrease in the fluid's potential energy. So, to state it in layman's terms, okay, you get an increase in speed with a decrease in pressure. So, if you have a vacuum, right, that's a decrease in pressure. So, thus you have an increase in speed on the other side. So, think sucking a fluid through a straw. Okay, you are creating a vacuum, so thus the fluid actually wants to take speed and get up that vacuum. Does that make sense? Okay. I think we'll start here at Bernoulli's principle. Got about 15 minutes of class.